everyone, dear faculties and dear students. I, Dr. Jayesh Juramalani, Associate Professor, Civil Engineering Department. I feel great pleasure to welcome Mr. Arun Sankar, Head Engineering and Design Division, Post Tension Service India Private Limited, Vadodara. Sir has graduated and have pursued post graduation from the MS University in Civil Engineering Department, and Sir has also served the MS University from 2001 to 2006 as a lecturer in Applied Mechanics and Structural Engineering Department. And Sir has joined the Post Tension Service India Private Limited since 2006. So, Sir, today the topic is basic of the post tensioning in concrete structures. So without wasting further time, I invite the sir to deliver the talk. Sir, session is yours.
Thank you, Jayasji. Am I audible, right?
Yes, sir.
Okay. So, good afternoon to all. Hope you are doing good and your health is good. So this would be the most introductory phase of going through the pre-stressing systems. One of the pre-stressing systems known as unbonded post-tensioning system. We'll go through this in slide by slide, and we'll try to figure out where this would be the most you can say useful, and how it is actually carried out on site, and what are the basics. So coming to the you can say learning phase of the in college life, this could be the first example of maybe applied mechanics, or maybe your stress analysis, or any other applied mechanics related classes. So this is nothing but it is a classical example of simple bending action in RCC beam, wherein you have a beam which is supported on two supports. You can say one of them can be roller, or one of them can be hinge, or you can say simply supported. And when the load is there on the beam, it will try to deflect, or it will try to deform, right? So the deformation is shown here. You can see that the deformation part is shown here. So the beam will deflect like this. So ultimately, when I cut a section here, so what happens is, this is the deformation in, you can say, in that particular section. If what we are representing, this kind of deformation is also shown here, like this is the shown deformation, or you can say the basic actions behind this deformation. So these are nothing but the compression and tension. These are the actions, or these are the forces, or these are the stresses behind this kind of deformation at particular section of the beam. So here, as you know, there is a compression or compressive kind of stresses generated at the top fibers, and the maximum tension or tensile stresses are developed at the bottom fiber. And you can have a transition between both of them. So you can join both the, you can say, vertices, and you will get a stress distribution throughout the depth of that particular member. So, and we represent that part with this kind of diagram, right? Where you have a C or green phase at the top portion, and T, which is red, which is at bottom. Now specifically I have kept that green and red color. Green means it is under compression, and generally all our members are of RCC. There are steel members, there are other materials used, but in most of the cases we are used to with the RCC members, or you can say concrete members, which are reinforced. So concrete is good under compression. It has a very good compressive capacity, compressive strength, whereas it has not that comparable tensile stresses. And if we compare if we have M30 concrete, M30 grade concrete, so its characteristic compressive strength, FCK value, would be 30 Newton per mm square. That would be the value of concrete. Whereas the same concrete will have a different value for the tension kind of actions, and that is almost 1/10 of that compressive strength. So it has hardly around 3 Newton per mm square will be the tensile strength. So there is a huge gap between the compression capacity and tension capacity of concrete, and we need to take care of both the actions, but predominantly the tensile kind of actions in the concrete member. So that is why actually I mark tension as a red color, because we need to watch out that, and we need to provide sufficient reinforcement to take care of that tensile kind of actions in the concrete member. So this is the basis of reinforced concrete members or RCC members. Now that is one step. The second step, or you can say one step ahead from that mechanism, is known as prestressing. Now what we are doing in prestressing is actually we are trying to introduce some stresses internally before it is subjected to its service loads. So that is the meaning of the pre-stressing. And how the pre-stressing would be done, or how the force, or you can say internal actions, how the internal actions are generated, will see in next slides. Actually what we are doing is we are trying to balance the stresses what we see in last slide. So there is a compression, there is a tension. We try to nullify, or we try to balance those stresses, and we try to minimize both the stresses, such that overall scenario may be you can say optimized, or you can say uh, economized to the its well extent. So that is the actually purpose of the pre-stressing. Why we are using pre-stressing is to reduce or to minimize the stresses or internal actions in a particular beam or slab. This is one of the you can say mechanisms of pre-stressing, which is known as pre-compression. Here, as pre-compression can be easily explained with this example. This is a, can say, favorite example of Professor Gustav Magnell, who has done a lot of work on pre-stressing, and he explained this mechanism of pre-compression with the help of a stack of books. You have a rack of book, and then if you just remove the rack or support, what will happen to the book will fall down, right? You cannot hold the book without rack. But there is another mechanism by which you can again hold the stack of book by having enough compression forces in both the directions, from here and here. You can again have a hold of the books, and this is nothing but it is a pre-compression. It is helping to a good extent in a pre-compressed member, or you can say pre-stressed member. This was one. The second one is known as load balancing, or you can say it is a weight balancing concept. Here the cable or pre-stressing cable is placed in such a way that it actually balances the gravity forces. So here as there is a continuous beam, wherein you have one support here, second support here, and third support here. These are the supports, and there is a beam running between those three supports, and there will be loading on this beam. So the direction of loading or gravity forces will be in this direction. These are the gravity forces acting on this beam. Now and this gravity forces will induce internal stresses, as we see in the earlier slides of basics of the bending, or you can say moment consideration, or you can say bending actions, wherein you have a tension in bottom, tension at bottom, and compression at the top at the you can say mid portion or mid span portion of a beam. So similarly, you can say these are the forces that are responsible to generate those kind of stresses in the beam. So here, if we can nullify or if we can balance these forces by having some kind of upward forces, you know, so that will nullify or that will balance, then that will minimize this effect of these forces. So by having this kind of you can say profile, these are the profile of a cable. This is a profile of the cable which help us to generate load balancing uh, forces, and that will balance partially, that balances the gravity forces. And this has been developed by Ty Lin. He also has you can say worked in the field of pre-stressing. So overall, this would be the summation of all three aspects. One is the RCC beam. Second one is the same RCC beam. Now it is having a pre-stressing effects. So you can see here. You can see that there is a beam, and that beam is having a cable inside. So this is a cable, blue color cable, right? So cable is having a particular profile. So it induces both the actions. One is known as pre-compression action, other is known as weight balancing actions. So because of this anchorages, at the ends, there will be a force generated through the anchorages that will be of compressive nature. So that will induce this precompression, and this cable profile, the profile of the cable, will generate this kind of weight balancing actions in the member. Now here, there is a role of eccentricity. We'll see what is eccentricity and role of eccentricity. Actually, the eccentricity is here. If you are able to see the zoom part here, if I see, this is the eccentricity from the straight line to this curvature line. Okay, what is the distance between straight to curvature line is the eccentricity. We'll see that, and how it is actually useful, or what is the contribution of that, we'll see in the next slides. So you must have seen such bridges or images of these bridges. This is nothing but it is a suspension bridge, and this is actually a well-known bridge in California. Uh, this is a Golden Bridge and Golden Gate Bridge, and this is in San Francisco. Now here we will go with the some of the you can say dimensions of this beam. So this is the same beam, same bridge with the dimensions. Now here the peer to peer, the dimension is from here to here. It is 1.28, means around maybe 1.3 kilometers. So the distance between these two, this is 1.3 kilometers. There is no support in between this 1.3 kilometers. Whereas the height of the bridge, you can say, is 230 meter, right? So 230 meter, if you want to physically realize this value, it's something but it's around 75-story building, right? So why to go this much height? And again, this is from the main sea level, 230 meter. So it is having 75-story building equivalent height of this pier. Why to go with this much height of the pier? There is a you can say magic behind this number. So we'll see that. So this 230 meter is required to achieve eccentricity of 150 meter. Now here 150 meter is nothing but if you can realize this number, 150 meter is equivalent to 50-story building, right? So uh, why this 50-story building and equivalent eccentricity is required is nothing but to take care of this span. The span is so much that this are required, right? So eccentricity plays a bigger role in everywhere. Actually, whatever we see, in bending actions, eccentricity is there directly or indirectly. We'll see that in next slide how it plays a role. Now same cable, and we have certain eccentricities. Now we are bringing the same concept in our you can say beam. So let's have the beam, right? And here the same cable, you can say the eccentricity would be different, but we can match those fundamentals here as well. Now here you have RCC beam or RCC slab or PT slab, and here the eccentricity plays a role. Over there, you can say a 50-story building equivalent eccentricity was available, but this is not the scenario in case of our buildings and residential. Either it is residential or commercial. Always you can say architect or builder wants this thickness or depth of the beam as minimum as possible. Now to reduce this depth or ultimately the eccentricity or depth of the member, we are hurting some of the design parameters. One of them is deflection, or you can say deformation. Either it is a elastic deformation or long-term deformation or instantaneous deformation. So to take care of this deformations, actually, for a less depth, the deformation would be more. There are L by D criteria given in the code. IS 456 code is there to make sure about the minimum criteria and all design requirements for RCC buildings. So if we refer that the span by D ratio, there is a L by D ratio given in the IS 456 code, which is for continuous beam it is 26, for simply supported beam it is 20, and again this is restricted up to 10-meter span. There are factors to be applied if we need to increase the span, and accordingly we have to at least start with those depth values by comparing with the span by D ratios. So there are specific span by D ratios. So for specific span, that minimum depth is required, but this would not be the actual case when you go in practice. Client always wants something extra, something more, something you can say well valued engineered, you can say. So as a part of value engineering, what the most client wants is to reduce the depth. So to reduce the depth in RC member, it is next to, you can say, it's difficult. So the easiest method is to introduce PT in that case, when there is a requirement of having lesser or depth need to be minimized. The PT has to be there, and the PT does its role in very well, actually. So here what happens is we can have this upward thrust, and by the help of this upward thrust we can minimize the actions of downward force, and because of that we are able to minimize the depth of the member ultimately. So this is one of the advantages of having post tensioning or pre-stressing. Other advantage is related to its durability, or you can say crack control. We'll see in the slides. Let's go with this weight balancing concept in detail, just to make sure, or just to visualize how it works. This is an example, or you can say exercise you might have carried out in your laboratory classes, wherein there is a string. The blue is a string or a tie member, you can say, and uh, uh, there is a roller or hinge here, right? And tie is actually subjected to certain weight, so it is UDL, and it has a certain you can say counterbalance on the other side. So that is the weight, or that is a force actually in the string or in the cable, blue color cable, right? So for a particular weight, for a particular counterweight, there will be a particular you can say sag, or you can say particular eccentricity for a particular case, right? So that will be you can say the system will be under equilibrium with certain eccentricity, certain weight, and certain counter balancing force. Now here, if I need to decrease this E, because always there is a case that we need to decrease the depth of the member. So by decreasing the depth of the member, it's nothing but we need to decrease the eccentricity. And if we decrease the eccentricity, what happens is, let's see. So your counterbalance force, or your force in the cable, or force in the member must be more. So your force is more, then you can achieve less eccentricity, and ultimately you can achieve less depth of the member. So that is the beauty, or that is the magic by which we can reduce the depth of the member. The same thing here, it is almost the same thing. There is a weight in the, and there is a string, and there is a pulley. So when the weight is coming, it will get a sagging. When if you need to have a balancing force required, then you need to introduce some more force in the cable, and this is how you can eliminate the sag, and you can reach to its nearby the approximately the same location. It's not absolute, but relatively you can reduce this eccentricity. So in nutshell, now you have all three actions here. This is RCC stress diagram, wherein compression at the top and tension at the bottom. This is the pre-compression due to pre-stressing. This is weight balancing due to pre-stressing. And overall scenario of these three is nothing but this is the net behavior or final stress diagram, wherein you can have control over your stresses, whether it is a compressive stresses or whether it is tensile stresses. You can control those things, and here there is a very less tensile stresses. Now there are limit of the tensile stresses permitted in our code, like if it is a water retaining structure or something related to that, then there could be a zero tensile stresses that also can be achieved with the help of pre-stressing. And in case of buildings, there are some tensile stresses are actually permitted, like 3 Newton per mm square is permitted for type 2 design. So up to that, we can permit, and we can economize the structure, or you can say we can have a better or durable structure, because once the tensile stresses are less, your cracking in the concrete will be less, and ultimately your reinforcement will be protected. And once your reinforcement is protected, your durability aspects are better. So these are the classification. This is the classification of pre-stressing systems. It has a pre-tensioning system and post-tensioning systems. So pre-stressing is a general term, and pre-tensioning is a part of pre-stressing. Pre-tensioning means concrete will not be cast first. First, the cable will be stressed, and once the cables are having the force inside, then with that force inside, the concrete will be cast, and then once the concrete reaches its required strength, then the force is transferred to the concrete uh, by cutting the, you can say anchorages of the uh, cable at the ends. Whereas in post tensioning, what happens is your concrete once your concrete reach certain strength, then we are stressing the cables are laid before casting, and we need to wait for a certain days so that the concrete reaches enough strength. Once it reaches enough strength, we can stress them, the cables. So that is why it is known as post tensioning system. Means we are stressing after casting of the cable or of the beam or slab. In post tensioning, there are two subclasses. One is known as grouted post tensioning systems, or you can say bonded PT system, and other is known as unbonded PT system. Uh, in India, the bonded PT system or grouted PT system is there since long, and actually this unbonded PT system is nothing but it is evolved from the same like bonded PT system in USA and in 1950s 1960s, and since then it has been successfully used in USA and across the world. And now we brought this technology in India in 2006, and since then we have completed more than 1700 projects with this system, and uh, uh, with this profile I'm going ahead with this unbounded PT system, how it looks like and what are the nuts and bolts of this system. So this is an icon of the unbounded PT system, wherein you can see the anchorage part of the PT system. A cable, blue color cable is there passing through the slab or beam. There is an anchorage at the end of the cable, or where your element is having you can say the end of that element, and at the end you have this kind of anchorage assembly. This is all like you can say advantages. PT can reduce the concrete volume by a certain extent. Formwork can be stripped off. The shuttering can be removed around 6th or 7th days after casting. Generally, our casting would be on uh, 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 you can say stressing would be on maybe on 5th or 6th or 7th day based on the concrete strength gain. Once the concrete reaches 25 Newton per mm square, we stress the cable. So around 7 days we can stress the cable, and after stressing the cable we can remove the shuttering. So it would be a faster way of constructing let's say buildings. You can have a more larger spans, maybe around 25 to 30 feet spans. So your column to column spacing would be accordingly. You can avoid some columns. You can have you can say you can avoid the obstruction in the building. Also, there is a stress control, so your reinforcement is protected, and that is how your actually maintenance cost would be less, and overall life of the building will be more. This is a brief history of post tensioning. The first patent was being registered by P. Ejections of San Francisco in 1886. Then in 1928, Fressinet has started playing with this, you can say, schemes or fundamentals, and he used high strength wires and concrete, and he started experimenting on this and using the technology on his projects. Or then in 1939, the same President guy has again developed something which is nothing but the wedges and special jacks for stressing. These are the key developments, you can say. Then there was a World War II after that, and during World War II there was a scarcity of workforce, humans, as well as there was a scarcity of infrastructure. There was a huge loss of buildings, bridges. Everyone was not having enough infrastructure, and now there was a scarcity. After World War, the scenario, post World War scenario was such that there was no material left for using them in building the infrastructure, and there was a huge scarcity of metal, steel. So then again post tension or pre-stressing came in picture. So and again there was an experimentations how to use the pre-stressing in the buildings. And in 1949-50s, first bridge was constructed in Philadelphia, the Walnut Lane Bridge, and this was the first application of PT in USA in 1949-50s. Then in 52, the first use of the PT in building, that was in Colorado, and it was for a cold storage warehouse building. In 1960s, people have started using them, experimenting them in nuclear containment also, and this is how it has introduced its level of excellency, or you can say quality, which can be applied in case of nuclear buildings. In 1970s, there was a ductile iron casting technology that has been developed in the metallurgical field, and that has again lead us in developing a good anchorages, and that is a good, you can say, key development that has helped us in developing, you can say, good anchorages systems. And then in 76, there was a formation of post tensioning institute, and now this is you can say one of the regulatory bodies across the world internationally, which guides us about what to do, what not to do, and they have prepared well good specifications, and the systems of pre-stressing. And if you follow this system, I think that would be, you can say, error-proof system, and that will turn out to be most economical and most, you can say, efficient system. These are some of the state-of-the-art developments or key developments. One of them is the specification developed by the PTI regarding unbonded system. The system of extruding plastic sheathing around the grease and strand. What you see, the cable, the structure of cable right now, this is nothing but it is the same thing, the system of extruding plastic. So this cable is made up out of this extrusion process, and it tells about the extrusion process. Then ductile iron casting, as we seen in last slide, concept of weight balancing, banded uniform layout for two-way slab systems. We'll see this in one of the slides. And computers for analysis and design. So we are able to make all the analysis and design faster by having the computers. and then now the encapsulated unbonded PT system is there. So it works well in the corrosive environments or highly corrosive environment where corrosion is a huge problem. You can use this. In fact, we are starting this encapsulated unbonded PT system as a default system in our case, and maybe from uh, April, we'll start 100% encapsulated systems to our clients. This is how it looks like. These are the components: PT cable, then wedges, anchor plates, pocket former. These are the components, or you can say fixtures, that are being used in the system. And the below is the uh, uh, actually view of the cable, how it looks like. There is a, and the presentation of what is applied to that. There is a HT stand, that is nothing but high tensile steel wire, twisted together, 7 wire twisted together, and having a strand. This is a strand. You can see the cross section view, and these are the 7 wires, and on that 7 wires, grease coating is there. Now this grease is having two purpose. One of them is to protect the cable from corrosion. So it is anti-corrosive grease. It is a special grease. And then it has another property, that is to have to give enough lubrication to the cable so that it can be stressed easily from the ends, and it can be moved axially. So that is why the HDPE stitching is there to make it unbonded over the grease, and the cable is free to move inside this HDPE grease, and due to the lubrication of this grease. Uh, the encapsulated anchor system is also shown here. The only difference is it is well protected against corrosion. So all the metal part is well encapsulated, or you can say well encased by the plastic, HDPE plastics, and that this is how we can protect the cable, protect all the material which can corrode, and it will be you can say more durable system. This is a schematic layout. Uh, you may see a part of the portion is already cast. This part of the portion is already cast. The cable is already there inside, and now the length is too much. Say this length is more than 100, maybe 200 feet, right? So in that case, we need to split them, and this is a, you can say, construction joint here. So this portion is already cast. This portion is yet to cast, but already ready to cast. Everything is laid, like reinforcement and PT cable and all accessories are being laid. So these are the intermediate anchorages, and uh, after reaching enough strength in this cast member, we can stress the cable. We can remove the pocket former first. We can place the wedges. After placing the wedges and after cleaning everything, we can start the stressing by stressing jack. Once it reaches to the required force, these wedges are self-locking. So these are having one-way action. So it will be self-locking once the stressing enough stressing is applied to the cables. So once the stressing is done, then the remaining part of the cable can be cut off. So this is how the system, or you can say the process, can be repeated to each and every cable. So same thing here. Here also the cable can be stressed, and then this portion can be cast, and again we can move on. These are some of the you can say images from the site. This image is from the uh, site having a anchor plate, pocket former, then a part of cable taken out from the edge, or you can say from the side of the slab or beam for stressing. So you can see that these are having the grease applied on the cable. This is from the inner side. You can see the inner side, it looks like this. You can have a group of the cable, and group are separated, and each cable has its own anchorages. So that is why it is known as monostrand. So this uh, is a monostrand unbonded PT system. So, and at the end, at the fourth uh, image, you can see that cables are being stressed. Once stressed, they are cut. The cables are cut, and then the pocket former recess is patched up, and everything is well within this perimeter. There is nothing taken out. So afterwards, you will not be able to see whether it is PT or not. But when you go inside, you will feel that the column free space, and you can say unobstructive ambience will mm, it may be uh, easy to figure out that this could be a PT building like that. So this is one of the slides from the site. It is of the TCS building, Tata Consultancy in Mumbai, wherein they were having a flat slab with drop panels. So you can see the cable laying and steel detail of the flat slab kind of floor system. Some of the images from the slide. Now let's discuss about the applications in residential projects. This is a flat plate scheme wherein you have a slab and directly the support. There may not be the beam, intermediate beams from column to slab. So beams can be there in perimeter or certain locations, but there could be an area where there is no beam. Here or here there is no beam. So this is known as flat plate scheme. So this is a laying of the cable or schematic laying of the cable in flat plate scheme. You can see that. So this is nothing but you can see vertically the cables are separated, or you can say cables are uh, distributed, wherein in a horizontal direction the cables are grouped together. So this is nothing but the band and uniform cable laying, what I discussed in the earlier slides. You can see the image of the site. Here, you can watch out the profile of the cable. This is at low point, this is at high point, like that, right? And these are the band cables. Band cables are in this direction, and uniform cables are in this direction. You can see the elevation perspective of the same building. The clear floor height is 10 feet, and there is no beam inside. So same can be applied in the commercial projects as well. So flat slab with column drop panel could be a good option for a commercial project, wherein the column to column spacing could be 8 by 8 meter, or 9 by 9, 10 by 10, or 12 by 12 meter grid. So this could be a better solution when you have a two-way kind of support locations. You can see the images after casting, after removing the shuttering. You can see the flat slab from the bottom. This could be a flat plate in commercial, wherein few beams are there in perimeter. These are the beams in perimeter. There is no beam inside. There is one beam here, like that. There is another set of geometry that is known as wide shallow beams with slab. Here you can see that the spans or column locations are that such that this is the maximum spanning and this is the minimum spanning, right? So in Maximum spanning, we have gone with the wide shallow beams, wherein the beam depth is less than the width of the beam, like this. This could be the section. This is the depth of the beam, and this is the width of the beam, and this is the slab thickness, right? So here, by achieving this, what we are achieving is nothing but reduction in the depth. Overall depth of the deck, or you can say floor, can be minimized by having such a kind of geometries. Here in this case, beam with slab, client was not having any problem with the beam depth. It was in RCC initially, in design. During those RCC design, these are the columns here. With this column, whatever the beam depth and beam width was there, we try to check without this column, and without increasing the depth of the beam, and we are just only increasing the width like little bit, we are able to achieve the desirable design, and that is how we opted for this by removing this column, and client was more than happy by getting uninterrupted space in the entire floor. This is an industrial structure where in ribbed beams, means beams are there in rib. You can see that closed ribs are there in this direction. All the beams, there are few columns like this. Alternate rib is having a column. So these are the columns. So here the span, this span is around 20 meter. Then here the span was around 12 meter. Here 16 meter, like that. So here only the PT beams in the larger span part, was being actually designed, and it was having a huge load on the floor. This was for Volvo Eicher workshop in Pithampur in Indore. We'll see image if it is there. Yeah. So this is the project wherein you can see that the floor, this floor is PT floor, and floor above is a roof which is steel. This is steel, a lightweight roof. So this floor was operational floor, and it was having a huge load. So that is why and the spans were more. This is 16 meter. There is a 20 meter inside, like that. So this is a unique structure. We were actually involved in having a waffle grid slab, wherein in slab, the beams in both the directions, and columns are only 8 columns, 4 at corners, 4 at edges. So this is how the structural system is. Only 8 columns. These are all actually cutouts, or you can say openings, and from column to column the spanning was around 120 feet by 119 feet. This was 124 feet actually, and this was 119 feet, 119 feet. This is in Jaipur, and they were having a constraint of the height of the building. They did not want to go beyond the existing building or existing temple just adjacent to this, and it was for Govindaviji temple in Jaipur, and they wanted to have a satsang hall just beside that temple, and they wanted to make it you can say lesser height than the height of the temple. So ultimately the depth restriction was there, and we could minimize the depth, and it went through based on the client and architectural requirements. So this is the image of the same building. You can see that it has been in operation. The year of completion is 2009, and you can see the hugeness of this building. Actually, this has won the Guinness World Record of having the largest roof, flat roof in the world, having this much span. few iconic projects constructed with using this technology is one of them is this is the 40-story building, tower building, you can say, in Mumbai, in Lower Parel, for Urmi Estate. And we entered from the 19th floor. So from bottom to the 18th floor, it is all RCC beam column grid, and from 19 to 40, it is a flat slab grid. So there is a core wall in the central part that is taking care of the lateral actions, and there are columns at the perimeter, and there is a perimeter beam like that. This was the geometry, and we introduced PT by removing the beams. The beams were actually joining core wall and this perimeter columns. So we tried to optimize them, and because of this, they could actually increase some more floors in the total height of the building by removing this beams actually. This is one of iconic buildings we did. It is for TCS, Tata Consultancy Services building in Mumbai. This is a phase 1. Phase 2 is also completed, and now we are working on phase 3. So it is a huge campus in Mumbai for TCS. This is IT Park in Mumbai. We completed this this is a flat slab scheme. You can see the podium, and the building tower. This is one of the commercial complex in Ahmedabad for Shivalik Group, and you can see the geometry and some inclined columns and all these stuff. This is a campus development for Sandeep Foundation in Nashik. There are classrooms, there are other infrastructure buildings like laboratories and library block and admin building. So we completed this in 2013, and it's working well. This is corporate building in Vadodara. You can see the iconic shape of the building. So you can have any shape, either it is in plan or elevation. So there is a flexibility of having such shapes in PT. Again, there is a high-end flat scheme in Vadodara. It is known as Cloud9. You can see that building maybe few other floors yet to cast, but it is on the structure is ready. You can see it is a flat scheme. This is a corporate house for Linde engineering company. Before this, it was there in L&T Circle. They have moved to this new building now. It is in operation since maybe around 1.5 years. So ultimately, it looks like this. All the things are inside, nothing is taken out. So everything will be flushed inside. So you are not harming anything, your facade or whatever to be. There is no limitation or making a facade or something like that. So everything can be flushed inside, and it looks as good as your RC buildings from the outside. So thank you. If you have any questions, please let me know.
Thank you very much, sir. You have given in-depth knowledge about the pre-tensioning systems, and also share with us the various projects which are completed using this. Thank you very much, sir.
Okay.
In future also, we would like to invite you for the further example and further detailing of this same system.
Sure. All right. if you have any questions, we can discuss right now.
Sir, one question has been asked that any difficulty we are facing or you have experienced in any of this tall structure while installing this system?
In tall structures, actually, there won't be. This is the easiest way of, or you can say, this is the most flexible method of prestressing we come across. So
Okay.
this is the most flexible. So here the cable is also flexible, and the anchorage system are individually accommodated. So everything is flexible here. So as such, there is no trouble or nothing like difficulty in laying the cable. But only difficulty can be when the concrete doesn't get enough strength, right?
Right.
That is the you can say indirect difficulty or indirect limitations. So if we are not equipped well, as far as concrete is concerned, then there could be a difficulty in stressing. Otherwise, if we get enough strength of the concrete, as per the design requirement, there should not be any problem with the system.
Yeah, that is great. So proper care should be taken while
Concreting.
casing concreting.
Yeah.
Thank you very much. Okay, on behalf of Parul University, I would like to thank you, Mr. Ranu Sakar. Despite a busy schedule, sir is kind enough to accept our invitation and deliver the talk. And sir has shared his experience and knowledge with us. So again, thank you very much. Thank you, sir.
So thank you, Jay. Bye.
Bye bye. Jiten sir, I request to stop the recording. Jiten sir, please stop the recording. Jiten sir.
All right.
All right. Thank you very much, sir.
Yeah. Bye.
Bye. Jiten sir, please stop the recording. એને ફોન કરો ને